Okay, I'd like to start by thanking the organizers for this opportunity to give this talk. So I should point out this is work with a large group of people. So we have people from HEP-PH, people from Astro-PH, and we also have people from HEP-TH. So it's quite a diverse group. So let me start by saying that string theory may be in a sort of physics limbo at the moment. It has never really come to terms with dark energy. And by dark energy, I don't mean the cosmological constant. I essentially mean something that's there in these data sets. So we see it in supernovae, we see it in the cosmic microwave background, and we see it in BAO. And we don't know if it's a cosmological constant or it's some sort of, effective fields theory with a scalar field, like a quintessence model. It could be modified gravity, it could be various other things. So we should just keep everything open. For string theorists, basically back in 2003, KKLT gave a construction of a de Sitter vacuum. But since then, it seems like the community has been scrutinizing this framework and essentially tearing it apart. And so now it's not clear if there is an embedding of de Sitter vacua in string theory. And so this has been kind of absorbed, or at least this absence of de Sitter, this idea has been sort of absorbed into the Swampland program. And so what the people in the Swampland program are doing is trying to basically characterize what good low energy effective field theories should look like, at least the ones that you can UV complete to a quantum gravity theory. So this is a very active program within string theory. And they've made a series of interesting conjectures, and some of them are quite formal and theoretical. But then the most consequential, at least for cosmology, is the one that basically precludes lambda. And then this is at odds with Lambda-CDM. Now, it's actually not a bad time for string theory to be weighing in and sort of saying, well, okay, maybe there's a problem with lambda. Because there's certainly stuff going on. So if you look at basically all these observations here that basically have been compiled by Eleonora, there seems to be a mismatch between inferences of the Hubble constant that basically make use of a cosmological model. So in this case, like Lambda-CDM or equivalent, and then stuff that basically is based on local determinations, which are essentially agnostic to the cosmology. So I guess the most competitive determination at the moment we have is basically due to Adam Rees and collaborators. And you can see that their determination here is more or less representative of all these other determinations over the last few years. They're essentially combining Cepheids with supernovae. We have tip of the red giant branch with supernovae. We have various other things. It's just interesting to point out the time delay strong lensing here with quasars, that basically there's numerous different determinations, some of which are consistent with Planck and others which are consistent with Rees. And yeah, so it's quite interesting. It's relatively fluid, but I mean, if you look at these determinations, at least the local ones, it does seem to be the case that there is a preference for a slightly higher H0. Okay, and so one thing we should bear in mind is, I'm going to tell you that I think the local H0 is legit. But one thing to bear in mind is that Subaru and his collaborators, they're basically plotting their own course against FLRW. So basically they're looking at the assumptions underlying modern cosmology, and they're looking at the cosmological principle, and they would like to test this. So they want to test that the universe is isotropic and homogeneous. And in this recent paper, they make use of quasars, and they basically question, so what they find is basically the dipole, due to these quasars, although it aligns with the dipole from the CMB, there's a difference in the magnitude. So they're basically taking this as evidence to say that we don't live in an FLRW cosmology. And if this is true, then this is a very interesting twist. So we basically have these local determinations, which seem legit, and then you can try to basically incorporate them in a cosmology, and typically people make the assumption that it's isotropic and homogeneous at relatively large scales. And I'm just saying that basically there is a small caveat here and there is an assumption, but I think a lot of the work on the theoretical side in the literature is essentially based on FLRW. But just to bear in mind that Subaru is there as well. Okay, so what does string theory say? I told you that string theory is basically, it has a problem with dark energy, so it's not clear what it's going to say. So it's clearly, string theory has essentially not much to say, but the Swampland program, they initially backed quintessence. So basically, for the Swampland, there is no lambda. And then basically you have to look at the next simplest effective field theory, and that's essentially a scalar theory with a scalar potential, right? So this is some sort of effective description for dark energy. And so this was the original paper from 2018, which just followed on the heels of the original de Sitter conjecture. And since then, we've had, well, one of the co-authors of this paper, Paul Steinert, has basically, with some collaborators, that they've since come to the conclusion that extra dimensions and Einstein gravity are only consistent with late time cosmic acceleration if the null energy condition is violated. And so in the same paper, they also make the case that quintessence doesn't work. So it seems like Paul has now left the swamp, right? So this is kind of interesting because it's at least a theoretical argument that, you know, if you buy into the extra dimensions, and if you look at maybe low energy effective theories corresponding to string theory and higher dimensions, which should be Einstein gravity, that you would have a problem with quintessence. And so you can also see this on the data side, right, or the observational side. So it's well known that basically if you take Lambda-CDM and extend it by giving a constant equation of state for dark energy, essentially a W, and I should say for lambda that W is equal to -1. So now you have this extra constant parameter in WCDM. If W goes up, H0 goes down. And if W goes down, H0 goes up. So that's, I mean, this is, you know, well shown at this stage. And so you can ask, can you extend this to quintessence, right? And what would be guiding you here is basically in quintessence models, W is greater than -1. So you basically now have, instead of W being a constant, you could have W to be, it essentially depends on redshift, or it's time dependent if you like. And as long as W is greater than -1, you're in the quintessence regime. So there is a well-known parameterization of, let's say, a dynamical dark energy model called the CPL model. And in this, you're basically doing a Taylor expansion in essentially 1 minus A, where A is the scale factor. And you keep the first two terms, the constant term, which would be this W in the original WCDM model, and then you have an extra term, WA, which comes with some redshift dependence. So what's interesting about this is Sonny Vagnozzi and collaborators, they basically did some analysis back in 2018 and showed that, what I need to point out here is that basically this is their best fit for Lambda-CDM. So you've got a sort of a Planck value here, 67.5. But then if you basically move away from lambda and you restrict yourself to W greater than -1, which basically means W0 has to be greater than -1, and also W, so the assumption in this paper was that W0 plus WA has to be greater than -1. They took the limit that basically Z goes to infinity, because CMB scale is essentially 1100 in redshift. So basically they made these assumptions, and that you see that basically your H0 value decreases. Now the thing that I want to tell you today is basically that CPL is not generic. So essentially it's a Taylor expansion in 1 minus A. So if you had all the extra terms, it would be a generic model, at least in the quintessence sector. So when you describe quintessence, I mean, the equation of state isn't exactly fundamental, and what is fundamental is the potential. So you start with a potential and then you derive the equation of state. And if your equation of state is essentially truncated at leading order in 1 minus A, or Z divided by 1 plus Z, then it should be a relatively, as you go to higher redshift, basically it should be a more and more constrained quintessence potential. And there's a nice paper by Robert Scherer from 2015 that basically points this out. So basically, now that I've argued that this result is okay, so it's generic enough, but it should only hold for a class of quintessence models, you can ask, can I do a bit better? And so what you can do is you can try to be model independent, and you can work perturbatively in redshift around z equals 0, which is today. So, and you can more or less prove that if, at least in quintessence models, that because the W is going up, essentially that H0 is going down. So basically just backs up the intuition that you have in WCDM and in the CPL model. So I mean, the thing that you need to take away here is basically, in other words, if Hubble tension is cosmological, right? If it's not just something local, if it's not a breakdown in FLRW, then quintessence, which is the simplest dark energy effect of field theory, is dead, because it's always going to exacerbate Hubble tension. It's always going to lower H0 for you. So this is a very interesting, well, I think it's an interesting observation, because basically, you know, it's a question then of how partial are you to quintessence. But the basic idea is simple, right? So you write down your Friedmann equations, which essentially look something like this. So you've got a scalar equation. Now here, this, let me point out that there's a potential, V, it's a function of phi. And we also have a dark matter sector, and we have a baryonic sector. And then F is just some function of phi. So V and F are a function of phi. And this essentially is the coupling. So we're basically, if we set this to 1, then it's just uncoupled quintessence. And if this is in some function, then we have a coupled quintessence model. And the perturbative argument is quite easy. So basically, these are derivatives with respect to time. So basically, you can go from time to redshift in this fashion here. And then once you do that, you can essentially solve these equations order by order in Z. So we have a scalar, and you take its value at z equals 0. So it's phi minus phi 0. And you just expand it order by order in Z. So we've got a Z squared, Z cubed, and we didn't go any further than this. So we drop these terms. And then, because basically you're working at low Z, these essentially phi minus phi 0 shouldn't be too big. So then we can also expand the potential in phi minus phi 0. And again, because of essentially we were motivated by the Swampland conjectures, which essentially pertain to the first derivative and then the second derivative of V, we didn't go any further, but basically this is the general idea. So basically now, if alpha, beta, and gamma are equal to 0, you get back the Lambda-CDM model. And then for any alpha, beta, and gamma in the vicinity of 0, 0, 0, you then have a quintessence model. So what we did is we took these, we basically solved the equations of motion, and then this defines the Hubble parameter. We go back, so we plug it back in here, we get our Hubble parameter, and then we fit that to some data, and we basically fitted it to baryon acoustic oscillations, cosmic chronometers, and type 1a supernovae, which is just some relatively standard compilation of cosmological data. And because we're working perturbatively, we kept this below 0.7. And so what we found is, like, this is essentially a very large class of quintessence models. And here, at this point here, is essentially Lambda-CDM, where alpha, beta, and gamma is equal to 0. And the models where basically H0 goes up, and they certainly exist, the chi-squared always goes up. So there's no exceptions to this. And only the models where basically H0 goes down can we perform better than Lambda-CDM with respect to this data. So basically this data only likes quintessence models where H0 goes down. So if we're in those models where H0 goes up, the data doesn't like it, right? And so basically, this was the uncoupled case, but it turned out that basically you can have a very small exponential coupling. So basically, if you take f to be the exponential of some constant times phi, then you can repeat this. And again, what we found, we were basically working at low redshift, is that basically the coupling, assuming the coupling was consistent with some bounds given by Harry Desmond et al. In this paper, it didn't really affect our conclusions at all. So basically, we didn't find any quintessence models. Roughly, this is like a scan of 100,000 models. We didn't find anything in the vicinity of Lambda-CDM where basically H0 would go up with a small exponential coupling. Now, so basically that sort of says that, you know, this original Swampland conjecture, that sort of, okay, the de Sitter conjecture is fine, but basically quintessence may not be a good bet, right? Because it's just going to exacerbate Hubble tension. Assuming again that it's cosmological. So to deal with Hubble tension, you will have to look at some sort of coupled dark sector. So you should take your quintessence model and have a coupling to dark matter. I mean, we attempted to do it here, but basically our coupling wasn't big enough and we didn't turn it on early enough. So this is a paper by, actually an earlier paper by Cumran and his collaborators. And what they do is it's essentially a quintessence model at high redshift, and then basically around z equals 15, they turn on a coupling. And then this essentially causes your, well, I guess the baseline here is Lambda-CDM, but it basically causes your Hubble parameter to dip, and then it comes through the data much shallower than Lambda-CDM would do. And this means that you can get a slightly higher value of H0. And so I should stress that they took a particularly reasonably large values for C tilde here, which is their coupling, which is 0.3, and they get a very small increase in H0. So basically this is the Rees 1 sigma here. So it's just a marginal improvement. Yeah, so the coupling was turned on at 15. This was quite novel. I don't think people in the coupled quintessence literature had thought about this, but this has two immediate problems. First one is basically if you take BBN and you assume BAO physics as it's conventionally done, and then you assume that it's Lambda-CDM in the early universe, this is a very strong assumption. And this explains why you can't really improve this you can't increase the H0 value that much, is because basically somewhere around, I guess at low redshift, 10 to the 0 here, z equals 1 and below, you have all this BAO data, and that's been, the BAO scale is essentially, can be fixed by just the assumption that Lambda-CDM in the early universe, BBN and BAO. So you don't have to use Planck whatsoever. And again, here what we see is basically the BAO plus BBN result here, H0. And I think this to Rees is essentially something close to 3 sigma. So this is quite an interesting thing. I'll come back to it later. But the other problem here is that Desmond, as I mentioned, Harry Desmond has these constraints. And essentially they're roughly at relatively low redshift, I think out to 0.05 or so. But they tell you that, you know, delta G, or your effective Newton constant, that it really can't change by that much. And so basically in this model here, the effective Newton constant would be of order, I think, well, delta G divided by G would be of order 0.1, but the bounds here, at least for this model where there isn't any screening, would be a number of magnitudes lower. So let me tell you that just to sum up, ultimately, I think string theory struggles with dark energy. And the Swampland has not been able to address Hubble tension. I've given you two. I mean, I think this paper is essentially state of the art. And yeah, I mean, it just doesn't work. So, but in general, cosmological resolutions to Hubble tension have struggled. So as I mentioned, this argument of BBN plus BAO plus Lambda-CDM in the early universe is extremely strong. And if you take it at face value, what it does is it says that we need to change the BAO scale. And how we do that is we introduce some new early universe physics. So I think the earliest paper in this direction is this early dark energy model of Poulin et al. And it's very interesting. I mean, yeah, I mean, basically that you can infer from Hubble tension that there has to be some early universe physics or new early universe physics. This is something, yeah, it's a little speculative, but still it's quite nice, right? But just to point out that this appears to be at odds with large scale structure. So there's been a heated debate last year about, you know, whether or not, I mean, large scale structure likes this early dark energy model or not. And I've put a little smiley face here because when you talk to people who work on large scale structure, some of them are basically convinced that Lambda-CDM is the model. So basically Lambda-CDM goes in as an assumption in lots of places, right? So it's maybe not so surprising in some sense that large scale structure seems to be at odds with early dark energy, because there's a hidden assumption of Lambda-CDM all over the place, or that's how it looks to me. Okay, so let me make a very simple observation. So if Hubble tension is cosmological, then there has to be other H0 determinations within FLRW, right? So there's a very simple argument that we gave last year. So if you look at the Friedmann equations, you get this guy for free. It's an integration constant in the Friedmann equation. So usually when you solve it, the Friedmann equation, you get h of z. This term is on the left-hand side, and you get H0 as a constant, but we can rearrange it. And so what this says is there's some constant here, h of z, which is some observable. So it's something that you will determine from experiments. And then this is basically some integral over w of z, which is essentially the effective equation of state for your model. So it describes your model. But yeah, you have to make a guess for the cosmology. So this is what goes in here. This is the observations. And if you get it right, H0 will be a constant. So although mathematically it is a constant, and theoretically as well, of course, this is not guaranteed observationally, and you really need to check this. So basically now we can assume, right, that we have two models, and we have the h of z that's the same in both of them, and we can eliminate h of z. And what we will then find is that there's a ratio between these two Hubble constants, and it's essentially given by this expression here. So what it's telling us is basically if there is a difference in H0s, then that has to be described, or at least there has to be some sort of difference in the equation of state somewhere in an integral between 0 and wherever you're making the observation, wherever you have the data, basically. So in the early dark energy model, this would basically be happening in this delta W effective would be happening in the early universe. And basically in the late universe, you know, up as far as the CMB scale, you would basically find that these are consistent with each other. But on the flip side, if it's a late universe resolution that's required, then you will, I mean, there will be a discrepancy here. And so basically it's saying that, you know, there's a Rees value. We can take this to be this H0 of A here. And then there's a H0 of B that would be Planck. And then we know that at Z, which is essentially the CMB scale, they have to be different. But basically it tells you that because this is an integrated quantity, that basically at each Z that you measure it, in principle, you could see some sort of variation. So it's quite possible in some sense that you will see some sort of running of H0, at least within the Lambda-CDM model at low redshift, or wherever we're going to get data in upcoming experiments. So I think this is interesting. It's basically gives you, I mean, if we see this running in H0 within flat Lambda-CDM, you can just assume flat Lambda-CDM, then it would essentially tell you that there is no early dark energy, because what all early dark energy can do is it accounts for one particular value of H0. It can't account for multiple different values of H0. And the other thing to stress here is basically, if you just focus on the Lambda-CDM model, that's fine. I've told you that people who work on large scale structure, they love Lambda-CDM. They love putting it in all over the place. And, you know, basically it gets inserted everywhere in the assumptions. So you don't have, theoretically, you don't have to worry about this. We could just go out, you could basically, you apply Lambda-CDM to all the data that comes and then see if we can see any evidence for this H0. Now you can ask, you know, where is the evidence for this? Do we have anything currently that would be showing this? And it is quite interesting that the Holly Cow collaboration, at least in the appendix of the first paper, they noticed that their H0 determinations, that they differed across the lenses, right? So there appears to be something like a step function or some sort of descending feature with the lens redshift. In a later paper from that year, from 2019, the DES lens was added. And again, it's a descending feature. It's not too significant. It's roughly, let's say, I think this is 1.9 sigma. This may be 1.7 sigma. So it's certainly less than 2 sigma, the significance of this descending trend. But there is something in the data, and it's interesting to read into this. So we were motivated by that to basically try to construct, well, I mean, see if we could find something similar. Now, what we did is we combined some mega masers, and the mega masers are, you can think of as a proxy for Reese. They essentially are a high value of H0. So this is essentially explains the data in the first bin. But then the rest of the data is, so this is more or less a local determination. The rest of it is essentially cosmological data, and we've combined it and binned it in certain redshift bins. And what you can see is there is a descending trend, right? So at least it's not just this first point, there's basically these 2 points here. And there seems to be something. And again, this is not very significant. It's essentially 2 sigma or so. So I agree, this is completely speculative. And it comes with an extremely important disclaimer. And the important disclaimer is basically that the errors in the cosmic chronometers are essentially, they're essentially statistical errors largely. And so the systematics have not really been accounted for. And so these errors have been underestimated. Now, let me just tell you that the cosmic chronometers are essentially cosmological model independent. So this is a very good observable. So what you're looking at is passively evolving galaxies, and you're looking at the differential of, let's see, so you're basically looking at, you're trying to make a direct determination of H, which is given like is delta Z divided by delta T, right? So up to some factors, that's what you're doing. And there's nowhere where a cosmological model is assumed in this, although there is underlying, stellar physics that's assumed. So what's nice, well, I guess nice about this, depends how you look at it, is that we have some various model independent determinations of H0s that are based on cosmic chronometers, potentially with other data sets. And here's one due to Gomez-Valent and Amendola and Haridasu et al. And again, these error bars are underestimated, but essentially the central values are more or less consistent with Planck. So this here is discrepant with Reese at 3.2 sigma, go back. But again, the systematics haven't been properly accounted for. This later paper, again, I think Maresco is a co-author on this paper. So they've accounted for the systematics here. But even if you take the systematics into account, you're still looking at, because of the central value being here, you're essentially still looking at something that's approaching 2 sigma, right? So it's a 1.8 sigma discrepancy with a local determination. So just to take the takeaway here is basically that if you were just blind to the systematics, you would just claim that H0 is a local thing. Now, and even with the systematics included, okay, so this is not very significant, but if we can get, so I guess if we can get better quality cosmic chronometer data, at least we can find out if this number is it closer, is it under 70, is it over 70, or do the cosmic chronometers agree with Reese? It's quite interesting, and somebody should be working on this. So let me try to summarize. It's a bit quick. So Adam Reese knows a lot about data analysis. So as I showed you, he has a medal. We can trust Adam. I'm convinced that the local H0 is higher than Planck Lambda-CDM. I don't think we should doubt this. BBN plus BAO can eliminate Planck. So what's nice about this is you sometimes hear people who say it's systematics, right? So if you get rid of Planck completely by using BBN plus BAO plus Lambda-CDM early universe, then you still have a problem, and it's almost a 3 sigma problem. So nevertheless, so even though there seems to be some discrepancy here and it's robust, then string theory has problems with H0, and theory in general seems to have problems with H0 tension. Within FLRW, I try to argue that basically, at least for late universe resolutions, one would need to see a running of H0 within the Lambda-CDM model. And so basically, DESI, we've got a number of upcoming experiments, DESI, Euclid, they're all going to probe deeper in redshift. And in principle, we should be looking to see whether or not there is this running H0, at least within the flat Lambda-CDM model. And that's just binning the data. You can easily do, it can be easily done and checked. And I think this is quite an interesting, future direction. Is basically, cosmic chronometers. It is central value seems to favor Planck at the moment. And we should really look at this data set and get more, essentially get better quality cosmic chronometer data, and a competitive determination. If it turns out to be closer to Planck, then we would have a statement that this is really a very local thing. On the flip side, if we can get a higher value that's consistent with Reese, then it sort of says that we may be looking towards, let's say, a new early universe physics. So on that point, I would just like to leave it. So thank you very much.